Okay, so in this video I'm going to explain the snakes and ladders problem. So snakes and ladders is a very classic game. You start here, and you finish here. This is the goal. Oh, you always start at the first position. You have to reach the final position. So usually these games play between many people, but for this problem, actually for the actual game, what one person does is completely independent of the other people. So inspired on that, we wrote this problem. The idea was to know how many turns in expectation do you need to like starting at the first position to reach the goal. How many turns does it take? So you start at some point. Let's say that okay, so you for instance start in the first position. If you get 2, you will advance to position 3. You will advance here, and then you will climb the stairs and go here. And if you at some point you land in the head of a snake, like in the position 27 here, then you will have to go to the tail of the snake too, all the way down. So that's a part of the game. And just for advancing, you roll the die and you advance as many positions as the die tells you. And there is something else that you have to take into account. If you are near to the goal, let's say that you are right now, you're at position 28 here. If you get 1, then you will advance to position 29. If you get 2, then you will go to position 30. If you get 3, then you have to go back to position 29. If you get 4, then you will get back to position 28. And if you get 5, for instance, you will land in the head of a snake, and you have to go to the position 1. So it's just that when you are about to finish, you have to count backward. That's also something that you have to consider here in this problem. So okay, the solution to this problem, it's a classic expected value with dynamic programming. It's just that you have cycles here in the graph that you form, so you have to be careful about it. So as always, you have a base case for any dynamic programming solution, and you have a recursive case, the one that you have here, recursion. Okay, but the thing here is that this recursion that you have, as you have cycles in the graph, if you just implement the recursion like is explained here, then you will get an infinite recursion problem. So, of course, the idea was not to solve the problem using that. Okay, so for the recursive step, I'm saying that the expected number of turns that you have to take if you're at position X, it's equal to 1 plus the sum for all possible values that you can reach from X. So you will have, for all the possible values that you can reach from X, you take the probability of that action times the expected value of that action. That's actually a very classic problem of expected value with recursion. You have to consider here that d of x here, this guy here, means the set of all possible squares that can be reached from x after you roll the die. So the solution cannot be implemented recursively, as I told you before, because you have loops, you have cycles in this graph, so you will get an infinite loop if you do that. Okay, so basically what we have here is just the same equation that we had before, but you take the sum and you move it to the other side. I'll just show it to you. So you're taking this term here and you're taking it to the other side with negative sign. That's what I'm showing here. And basically what you did when you do that, you notice that okay, so this is an unknown and this is an unknown too. So you have some unknowns, you have a system of equations with that, and you can then write that system of equation as a matrix and then solve your favorite method to solve a system of equation. For instance, Gaussian elimination, or You can also use matrix exponentiation. That's another way to solve the problem. But okay, so one way to do it is just to use Gaussian elimination. For this problem, the board was at most 12 times 12. So you have at most 144 nodes. And it should be very efficient, an n-cubed solution. Like in this case, you will have a big O of n-cubed solution for each test case. That's fast enough to solve a problem, actually very fast. Okay, so some notes, something that you have to take into account is if you are at the end of the board, some squares may have probability 2/6 instead of 1/6 because you can't go back. And that what I show you here. If you start in the position 28, the little guy that I draw in that board, if you get, for instance, 1 or 3, you land in the position 29, so you have twice as much probability to land in position 29 that you have to land in position 30 or 28 or 27. So that's something that you definitely must consider to solve this problem. Like other thing that I told you before is that you can use matrix exponentiation instead of solving the problem with Gaussian elimination. If you use matrix exponentiation here, then the solution will have a complexity of big O of n cubed times log of n. That again is fast enough for the size of n that we gave here, so it's a perfectly valid solution to you, and it converges to the right solution. So okay, that's it.